It's my great pleasure to have brought Roger here many times, and he's come here to discuss some interesting developments, as you saw from the first talk. In the very basic case, Roger will explain, help a little bit about the complexity of the Howe correspondence of a finite field, which is what this is all about, and maybe set up the third talk where Sophie will explain some developments. Let me also say that Roger and Shomgaro are here until Thursday, but anyway, certainly all of tomorrow. And so any discussions that people want to have with them that might come out of this, or independently, if you have questions about Howe correspondence, he's here. So tomorrow, I think Roger will be in my office all day. And it's a great pleasure to introduce Roger Howe to the lecture. He'll talk about the Howe correspondence over a finite field.
Thank you very much for inviting me. I wasn't expecting an audience, actually. I'd like to start a little bit by talking about the size of representations. And I mean, the standard measure of size is dimension. And that's certainly a very important measure, but there are other ones which can be useful in various contexts, and I want to talk about one in particular today, which so it applies to representations of the classical groups, and I call it rank. And the idea is just, if you look at classical groups, you see, well, first of all, I mean, size of the first, I mean, dimension measures the size of vector spaces. I mean, it's the only sort of way to differentiate between two vector spaces over the same field is whether they have the same dimension or different dimensions. But then when you get into linear algebra, you start running into other things. And so in particular, you have linear operators and you have some notion of the size of them, and it's called rank. And what is it? It's, well, when you have a linear operator from one vector space to another, not everything gets hit. And the image of the mapping is some subspace, and it has a dimension, and that's the rank of the linear operator. So it's a useful measure of the size of operators, and there's other things, something like operators, which also have ranks. And it turns out that these ideas also can be applied to representations, because if you look at the classical groups, you see that they have large abelian subgroups, which are for which the idea of rank is relevant. So if you take GLN, well, all these groups have right parabolic subgroups. So like you can take a group, preserve some space of some size, and put it in a parabolic subgroup like this, and then this parabolic subgroup has what's called its unipotent radical, the things that sit up here with 1 and 1 here, and that's just isomorphic to a space of k by n minus k matrices. So the elements of this guy have a notion of rank, and if you look at the character group of this, the dual group, it's another space of essentially the same type. I mean, it also supports natural actions of GLK and GL minus K commuting with each other. So it has rank too. So you can talk about the rank of a character of this group. And then if you have a representation of GLN, you could restrict it to this group and then to this group, and you could say, well, what are the characters that appear? There'll probably be lots of different characters. Well, it's certainly not going to be irreducible. If the conjugacy classes of this under the action of the two diagonal subgroups is, matrices of a given rank can all be converted into one another by pre-multiplying by something in here and post-multiplying by something in there. So, a representation of GLK, of GLN restricted to there is going to be invariant under that action. So all characters of a given rank will either appear or they won't appear. So you can just ask, well, so what's the largest of the ranks that appear? And you can call that the rank of a representation of GLN. And you can, if you want the kind of the finest decomposition, you would make both of these guys as equal as possible. So either n over 2, or differing only by 1. So you could talk about this way. You can talk about the rank of a representation of GLN. And the other classical groups have similar structure. Okay, so if I take symplectic group next, sp2n, this contains so this is the isometries of a skew symmetric form, and so you have the notion of it for a skew symmetric form. You can pair two guys together and get any other possible number, including 0. So if you have a bunch of guys that all paired with each other to 0, they span what's called an isotropic subspace, and you can have isotropic subspaces of dimension up to n. So you can find a parabolic subgroup in here that preserves one of those maximal isotropic subspaces. And then you'll have these guys up here, and what these guys
contain.
Huh?
Contains.
Right. And then these guys up here look like, it turns out that they look like the symmetric matrices. And well, if you're over C, there's only essentially one symmetric matrix of each rank. But if you're over R, there can be several different ones depending on. Yeah, so you could again, so if you have some unitary or infinite, otherwise a topological representation of SP2N, you could restrict it to here, and you could say, what does it look like here? And it's, again, it's going to have to be invariant under conjugation, so it's going to have to just consist of guys in a certain number of orbits, and you can look for the largest possible orbit. You can call that the rank of the representation. And there's a similar idea for orthogonal groups. The orthogonal groups come in this family, you know, there's a compact orthogonal group, and then they can be, they can have isotropics at spaces of various dimensions. So that's a little more complicated, but if you take the one which has the largest possible isotropic subspaces, anyway, the idea of rank can go up to that dimension. Okay, so there is, you can have some notion of rank, and question is, well, I mean, it's not obvious at the beginning, are there any representations of various ranks? And I first came here in 1972, 73. No, 71, 72. So it was over 50 years ago, and Harish Chandra was here, and he was working. He had just recently proved his Plancherel formula that described the L2 space of a semi-simple Lie group. And if you think about it, anything that contributes to the Plancherel formula that's going to consist of L2 functions can only possibly have the maximum rank, because because all the lower rank guys are are proper subparties here. They live on lower dimensional things. They can't possibly be square integral functions. So if you're used to living with the Plancherel formula, it's not clear that there are any small representations. But it turns out there is, and there are, and they were relatively late discovered. And they come out. They, in fact, come out of the Heisenberg group, which Shamgar has just been talking about. So you take, so there's the Siegel, Shale, they, Oscillator, etc. Representation. And how does it arrive? Well, so SP2N of, so you take some base field F, X by automorphisms, on this thing Shamgar was calling the Heisenberg group. So this is a symplectic vector space. And then the group law is a two-step nilpotent group, and probably everybody knows it very well. And So you take two guys in here, and their group product is going to be the sum of them in here plus the commutator of them in here, half the commutator of them here. So this is an interesting group, which, I mean, it's not clear it's an interesting group, but it turns out it comes out of quantum mechanics, and it's very interesting there, sort of the basis, mathematical basis of quantum mechanics, which is why it gets called the Heisenberg group these days. Physicists, it was first sort of injected into physics by Hermann Weyl, and physicists call it the Weyl group. But we have something else we want to call the Weyl group, so we call it the Heisenberg group. And this has been pretty common terminology since the 1970s. Okay, so anyway, and as you know, as you heard from Shankar, this guy has, so HN has essentially a unique unitary irreducible with, so you take any non-trivial on F, which is the center. Yeah, this is the center of H. So, and then there's this basic theorem, which is due to Stone and von Neumann when F is real, and due to Mackey when F is in the other local field, that there's a unique irreducible representation of this group on which the center acts by that given character. So then if you let SP2N act by automorphisms, it's going to act trivially on here. So it's going to preserve that representation. So you're going to get a projective unitary representation of the symplectic group, and sort of a major part of Bayes' original paper on this was to so you get, yeah, I mean, you get a representation up to scalar multiples, and the question is how far can you eliminate those scalar multiples? And they showed that in the local field case, you could eliminate them up to plus or minus 1. So you get a twofold cover of the symplectic group. In that case, it's called the metaplectic group. And it turns out over finite fields, it's a little simpler, and you can just get rid of the scalars altogether, and you just get a representation, which I call the oscillator representation. I should maybe, the reason for that is that it is the analog, it's the symplectic analog of the spin representation. And the spin comes out of physics. It's the oscillator, I mean, this representation is very closely related to the harmonic oscillator of quantum mechanics. So that's the reason for the name, my proposal for the name. So Siegel and Shale had constructed this over R, motivated by quantum field theory, and then they did it over an arbitrary local field. Okay, so then you get this representation of the representation of many names. It's more or less an observation. As one. And in fact, the spectrum on spectrum on the center of this thing is concentrated on just one orbit. So if you're with a p-adic field and you have several quadratic possibilities, then there's only one of them. So this is a really small representation from the point of view of rank. So they exist. And then you can start taking tensor products of this guy. And the tensor, it's reasonably clear that the rank adds under taking tensor products, so that from the rank 1 guys, you can construct irreducible representations of all possible ranks up to the maximum. So, and it's also, I guess, it should be reasonably clear that the rank is pretty consistent with dimension. So the dimension, as you go to larger ranks, you'll also be going to larger dimension. So so it's another way of looking at size of representation. And so, well, then what can you say about the representations of a given rank? And again, the oscillator representation helps you out here, because here we want to talk about the idea of a dual pair. And
we are speaking of the local. You are speaking of the local field.
Yeah, local fields or finite field.
Because for finite, you can have 2 orbits. For finite, can
yeah, I guess there's only 2 orbits for finite. So what do I mean by a dual pair? So it's so you have a group G, and you look at a pair of subgroups H1, H2. The HI is the full centralizer of H2 or of HJ and G. So this is what I meant by a dual pair. And if you're interested in the problem of how does the representation of a group restrict to a subgroup, well, then if you take a group and a subgroup and you want to find out how representations restrict, well, the restriction of representations, any given representation, the isotypic space of that representation will be preserved by the centralizer of that subgroup inside the big group, and then vice versa. So it would be natural to extend the restriction restricted action to the product of the original group and its centralizer. And then, well, if you're looking at the centralizer, you can go backwards and you can look at the centralizer of that. And fortunately, that process stops at that point. If you look at another centralizer, it's the same thing. So, so if you're interested in the problem of restriction of representations, then the sort of the place to start is to look at products of H1 cross H2 where they form a dual pair. So in that context, this is a natural idea. And it turns out that it's a pretty good idea in this case. Let's see. So, yeah, so problem. Describe the restriction of omega, the oscillator page. Two dual pair. Yes. I'll say SP twiddle in case it's the metaplectic group. And so it turns out that, I mean, it turns out that the answer is pretty nice. And over local fields, so you have to work distributionally, but in a suitable distributional sense. Omega restricted to H1 plus H2 is equals bijection between appropriate subsets. H1 and H2. And here, I mean, you know, there's always a lot of technicalities in representation theory. And so these are what are known as the admissible duals of these groups. So there's a notion of admissible representation. And you make those are sets of representations that you, anyway, there turns out that there's a very nice bijection between, well, you only get certain representations of each one, but then it's bijected between those. But this, however,
and you have multiplicity 1 in
sorry?
You have multiplicity 1 in some sense.
Yeah, well, I mean, you know, these are not really, I mean, you know, they're not really sub-representations. They're, yeah, you have to look at things in a distributional way. So it's, but it's roughly speaking, I mean, that's the spirit of it, yeah. However, fails over finite fields. And I mean, so it's definitely not bijective. I mean, over finite fields, there's no technicalities about what the representations are, what the sub-representations are. I mean, they're just there. And it's just not a bijection. You can already see this for, I mean, the very simplest pair there is GL1 times GL1 inside SL2, or by GL1, I mean F cross of the. So that, and the action there is just the standard action of GL1 on the line, and there you have a copy of GL1, and then you have the origin, and so you get the regular representation of GL1 every character once, and then one more, the trivial character one more time. So you get two of the trivial character. So what to do? Well, it's here that the idea of rank becomes useful. So we observe that dual pairs come in well, in well, I'm going to call them a series. That's probably, I mean, in structured sets. So inside SP, like we have, what are examples of dual pairs? There's ON SP2M inside SP2 and M. There's GL and GL M inside SP2 and M. These are the main guys that make sense over any field, and then there's also unitary groups, and they also come in related series. So that if you fit one of these guys, it can be a member of a dual pair with the other guy, and the other guy can range over. So you can start small and you can let it get as big as you want. So and as far as the, like, if I take ON and I look at also ON times SP2M1 is contained in SP2N1, ON M2 is contained in SP2M2, and I can, if I want to, I can then take the sum of these guys and embed this into SP2N M1 plus M2, and then the sum of these two guys will get embedded in the SP2 M1 plus M2. So they come in these related series like that. And a key observation here is that the omega, we call it the oscillator representation. Anything one, and if so, let's see. If you pair so if you take SP2N OK as on SP2N consists of right. Okay, so so if you're interested in looking at representations of say SP2N, you can find representations of the various ranks by looking at the pairs with the orthogonal group with the appropriate dimension. And it turns out that doing this is very nice. And I guess the main theorem that I want to mention today is that if you're pairing SP2N with OK, it's actually not just simply representations of rank K, but in fact the representations have spectrum. So we talked about how the unipotent radical of a symplectic group consisted of symmetric matrices, and so there'll be matrices of rank K which correspond to this particular symmetric form, and so omega restricted to SP2N, which is contained in consists of reps with spectrum determined by OK. And then it turns out, this is part one. And then part two is that that there is a injection from the dual into SP and I should say, so here I want to, so this is for K less than N. Whatever you say about that. So you can parameterize the representations of the symplectic group of rank K when K is less than N by the unitary dual of the orthogonal group of that type. I think that's very nice.
This is all over the finite field.
Hmm?
We're in the finite field yet.
Yeah, that's right. This is, well, no, I mean, this is also okay over there.
But in particular, it's okay.
fields too, yeah. But in particular over the finite field, that's the place where it's most interesting.
When you speak of oscillator representative, you don't take the irreducible one, you take the two even and odd.
Well, let's see. No, you take one of them.
Thank you.
Yeah.
Can you explain a bit more what are you doing in one? So you take the oscillator representation on 2n+1 dimensional Heisenberg, coming from a 2n + 1 dimensional Heisenberg group.
Yeah.
And so can you explain what is this inclusion of groups? So I mean, the inclusion exists, but what does the theorem actually say? I don't.
That's part one or part two?
Part one. Can you explain what part one?
Yeah. Let's see. Well, I guess. Yeah. Well, I mean, the orthogonal group, right? I mean, you can think of the symplectic group as the dual pair sp201, and then the two. The two oscillator representations, two minimal representations, correspond to one of the two quadratic forms. Yeah. So with the picking of the quadratic form, you pick which representation you're dealing with. Yeah.
Also, in the first theorem, proper unit at most K is in the
Yes, right. Yeah, K is less than one.
no, I mean in the first theorem, when you say that it consists of permutation of rank K.
Right. Yeah, that's right. Right. That's right. Thank you. Yeah, so all right, that's the main result. And so it gives you, it gives you some way to talk about all these smaller representations that are you didn't see when you were worrying about the Plancherel formula or something. Yeah.
I think we conjecture that you get all guys of Renke and Sophie proved actually that it's
I guess,
Sophie,
yeah, right.
GLN we proved that it's exhaustive, but in GLN what you proved it's exhaustive for all guys of Renke.
That's correct also. Yeah.
Here, did you assume K at most N or not? You assume k at most equal to n? Or not?
Yeah, k less, I want it to be less than, yeah.
Exceptional groups don't fit into this picture.
Haven't figured out how to adapt this to exceptional groups now. You know, the dual pairs and exceptional groups have been classified by Rubenthal, but they're not. They don't come in. You know, they don't come in systematic series or anything, and I don't know what to do. Might be when somebody has a good idea, there might be something there, but I don't know what it is.
But you still have a notion of rank and some of the smaller rank for exceptional.
Well, so if you find, I mean, well, I have to confess, I have really not thought about that, but I mean, if you can find, you know, if you can find some thing like a group of matrices inside one of the exceptional groups, and a rank there, yeah. But I don't know. I mean, the one that I've and the one that I've looked the most at is G2, and that one, you know, that's really small rank, so only rank 2 itself. So
Before Sophie, I have a question. Since you've said that, but you mentioned to me at Yale a semigroup which you thought unified what she's going to talk about. Do you want to mention that before we talk?
oh,
After?
yeah, that's right. Yeah, so I got yeah.
What I suggest is it may make sense after.
It turns out that there's a way to so you get this injection. This works over finite fields also, but it doesn't exhaust all the representations. And the two members of the dual pair don't generate each other's commutants in that case. That result fails. But it turns out that there is an extension or a completion, I guess completion is probably a good word, of the symplectic group. Which we call the oscillator semigroup. So you can think of a symplectic mapping, a symplectic isomorphism, as if you look at its graph in the sum of two copies of W, the symplectic space W, and then if you put the negative form on the second copy, then the graph will be an isotropic subspace of largest possible dimension. It's called a Lagrangian. Okay, so the symplectic group can be thought of as the collection of Lagrangians in the sum of the symplectic vector space with its negative dual and with its negative copy, it's all the graphs. I mean, it's all the Lagrangians which do not intersect, have trivial intersection with either of the two copies. And then if you look at all the Lagrangians in the sum of the symplectic space and its negative, you get a larger collection of operators, and that's has a natural structure. It turns out, it's not obvious, but it turns out that it has a structure of semigroup. And that's the oscillator semigroup. And it turns out that if you have two members of a dual pair, then the one of the members and its centralizer inside the oscillator semigroup generate mutual commutants. So that leads to the question of what do the representations of these semigroups look like?
All right, so I think why don't we start at 5 past?